three indexes on the OBJ table, IOBJ1, IOBJ2, and IOBJ3. IOBJ2 specifically has, as well as the object ID like the other two have, it also has the object's name as well. So, and then depending upon the object type, if you're creating a table, there'll be a row inserted into the tab dollar and the col dollar tables, obviously for the columns of the table and for the table name and so on. If you're creating a function or a procedure, rows are inserted into the sources or the source table, source dollar, IDL, UB1, and so on. So when we create a given object, information about that object is stored all across the data file, the system, the system table spaces data file. And when the object is then dropped, just because it's dropped, it doesn't mean the information's completely wiped clean from the data file, and we can find evidence of this. So what happens is when the object is dropped, simply the flag in the row header of that row of data, the bit is simply flipped. Remember we spoke about that. The fifth bit of the first byte of the row header indicates something about the row of data, and if the fifth bit is set, it will become OX3C from OX2C. So we can then basically open up the system DBF file, and for each block of data that has a row, that is owned by has an object ID of the OBJ table, for example, we highlight every single one of those data blocks, and then using the row directory, check the offset. That will point to the row header. If it's 2C, it's not deleted. If it's 3C, it is deleted. So we block that out. We also block out the live rows in a different color. So what happens is eventually in the row data section, we have these nice little colored bars essentially with white space in between. Those white spaces will be fragments of deleted data as well. So we can essentially block out live rows, deleted rows, and fragments of previously deleted rows. And of course, we rinse and repeat for every single object of interest. For example, the sources table and so on. Now, remember we spoke about the indexes earlier on. When we drop an object, the index, like the IOBJ2 index, still maintains information about the object that's just been deleted. And so not only do we look at tables and so on, but we can look at indexes and so on too. So here's an example. This here is the row directory in there. This here is that's the row directory here. This here is the header stuff of the data block. Here and here is the object ID of the table that is filled in this this data block, and in this case, it's the sources table. Now, if we follow each of these directory entries, and down to the to where it points to in the file from the offset just there, we can see that this one points down there and that one points down there, and they all have 3C. The fifth bit is flipped in that row header. So we can see that all this data here is deleted data. We'll come back to this image in a minute. So after we think we've been compromised, so we open up the system DBF file and start going through each data block that is owned by this object ID here, which is the object ID for the OBJ dollar table. Now, we see here, after going through everything, that there is a directory entry just there that points to its row data, which is here, but we see that the fifth bit has been flipped, and it's 3C rather. So we know we're looking at a bit of a deleted row here. So we then need to crack out the data from that. Looking at the row header, we see it's deleted. That's the lock status stuff. We see that the third byte of the header is 0x11, which is 17 in decimal. So we know there are going to be 17 columns. This here is the data we'll be looking at, and we'll split it out. So given that we know that there are 17 columns, if we look here, that 04 indicates that the first column has 4 bytes of data, so we count 4 in, 1, 2, 3, 4, and then we get another 4, 1, 2, 3, 4, then is that a 02, so count 2, and then 0D, and so on. So you see how that's happening. We count 4, 1, 2, 3, 4, and then we come across another 4, so this is column 2, 1, 2, 3, 4. Column 3 is 02, so count 2 bytes, then 0D, and so on, all the way down. So eventually when we do that, we can break down our data into this format, like so. And we count the rows, and there indeed should be 17. Hope there are. There's 17 rows, 17 columns rather, split out. 17 columns, not 17 rows, my mistake. Now, knowing the way the obj columns are laid out, the first column is obj hash, which is the number, then the data obj number, the owner is next, and then the name of the object, and so on. So, knowing how to dump this data, C1 would indicate a 1-byte number, C2 a 2-byte number, C3 a 3-byte number, and so on. And this is basically the formula for getting it. So you take the number, subtract 1, multiply it by 10,000, take the next number, subtract 1, multiply it by 100, and then add, and so on. So you eventually get the object ID number is 51846, and the data obj number is 51846 as well. The owner is 55. We don't necessarily know who that is yet, because we would need to compare the user table with, that correlates to user 55. But we can see that there is, the name of the object is my temp table. And this is the date upon which the object was created. So this is the M time, the C time, and the S time. If we take that object ID and just do a simple binary grep through the rest of the system DBF file, we find this object ID is revealed elsewhere. For example, in the mon-mods table, the imon-mods index, the recycle bin, and this cluster down there. Now, once we've gone through all that, we start looking for evidence in the sources table and so on. Now, what happens is, when we come across that, this is the image we looked at earlier, we find that there's a deleted row, a bunch of deleted rows, by following, as we spoke about earlier, each entry in the row directory, you follow it down, from its offset. So we come across all this stuff. So this is the address offset in the system DBF file, plus that entry in the row directory. We go to that address and we find the deleted row. Now, when we look at these deleted rows, we find that they all have the same object ID, 51850. So we know that these deleted rows are all part of the same object. If we look at the text, you can see the text obviously in the ASCII text here. If we crack that out easier so it's easier to see, there is a function called extract syspassword return varchar, auth ID current user, pragma autonomous transaction, and if we look here, it's doing an insert into scott.myTempTable. That should obviously, we should be thinking, wait, myTempTable, that was one of those objects we saw dropped earlier, and it's selecting the syspassword hash and dumping it into that table. So clearly we're beginning to build a picture up here as to what's going on. This looks like Scott's come along, created an object, a function object that he's got all all the hallmarks of an exploit, i.e. auth ID current user, pragma autonomous transaction, and it's doing an insert. Pragma autonomous transaction is, hey, it's okay to run this go ahead and do this. It's not going to change the state of the database over whatsoever, but it is clearly because it's doing an insert into my temp table. So we can see that this is probably indicative of an exploit being run. Now, given that we know the object ID of the mytemp table, 51846 and so on, given that we know where that is, when we go through the other data files, we look at the users table space, and we evidence evidence of this table in the users table space. And we can see down here, that's the object ID there. This is the start of the data block. Here is the data that's been inserted. So that there is the password hash for the sys user. So we can see that someone has definitely exploited this, exploited our flaw to inject their nefarious function which inserts the sys password into a table owned by them. Okay. So that's how one would examine the data files themselves. Now, given that a data file might contain 36,000 rows, or whatever, of information we would need to search, it's going to take us a long time to do that manually. So eventually, I'm going to be releasing a tool called FEDS, which stands for the Forensic Examiner's Database Scalpel, that will automate all this process. So, unfortunately, I didn't get the time to get the tool written up in terms of releasing it today. But watch this space. So the next aspect of looking at a compromised Oracle server to ascertain whether a compromise is taking place, or if they have, what's the extent of the penetration, we can start looking at the Oracle redo logs. The redo logs exist so that in the event of a database failure, in other words, the system cuts out, for example, a power outage or whatever, then actions that were done before they were written to the data files can be redone. So the redo log contains entries, of course, and a redo entry contains all the given changes for a system commit number. The system commit number is, last time we committed to the system, the number was this, and so on. So all those changes are written in a specific redo entry. So there could only be one change, or there could be multiple changes. The redo entry has a header with one or more change vectors. So what do I mean by a change vector? Well, a change vector is an action that was taken before the database failed. So the operation code for an insert on a single row change vector would be 11.2, delete 11.3, and so on. Now, one of the interesting ones is DDL 24.1 down the bottom. For the vast majority of these lot, the